we just finished up the object-oriented programming section of lecture. Obviously still doing the homework assignments, but we're done with that content. And we're about to shift into functional programming. These two approaches are very different. I'll hesitate to say this definitively, but they're somewhat like opposite approaches when it comes to programming. They're distinctly different, they're very different. We're going to learn both of these approaches, and each one of these I have to artificially restrict you to kind of force you to use each approach. For each problem you solve, you would have choices, use one of these two approaches or some hybrid or some or neither. But there are two approaches that you can take when writing your programs, when designing your programs. So there will be a bit of a hard shift coming from object-oriented programming to functional programming. And then for the rest of the course, data structures, event-based architectures, and the project and the software engineering portion, for all of that, we're not going to have any artificial restrictions. At that point, it's, okay, you know object-oriented programming, you know functional programming. Some of the assignments, some of the lectures will use a hybrid approach. We'll mix them together. Actually, quite a bit of the course after this will mix them together. And when they're not, and when it's not explicit, use this or use that, that's where you get your choice. Is this a good spot for some inheritance and some polymorphism? Is this a good spot for immutability? Is this a good spot for recursion? Should I use my data structures? So after functional programming, it's more of, okay, I have these tools in my toolbox, and I have a problem to solve. Which tools do I want to use to solve this problem? So with object-oriented programming, the theme, the buzzword of the whole thing, the whole summary, summarized in one word, was state. Everything had to do with state. We have state variables. We have the state pattern. We have the values in the state variables changing behavior, and we have the types of the state variables and the types of objects changing behavior. Functional programming says none of that. We're not going to have any state. Everything's going to be purely mathematically defined. We're going to have this input-output behavior, and on the same input, you should always have the same output. Nothing should depend on state. To that end, or with that in mind, if somebody who's a functional programming aficionado would scoff at that definition, at that summary, but that's at least one part of functional programming. So to that end, we want to look at these three things: writing and tracing through recursive methods. I teased this a little bit earlier in the semester, and I said I'm not expecting you to write recursive methods, but we're going to trace through them and take a look at the stack and the heap as a recursive method is being executed. Now we want to start writing them. Specifically, Wednesday and Friday, we'll start looking at recursion. We won't see any recursion today, right off the bat. What we will start looking at today is using first-order functions, where a function, realizing that a function is just a value, and we will start using the word function here, not always methods. We'll still have methods, but there will be a distinction between a function and a method when it comes to functional programming, when it comes to this section of the course. So when we have a function, how do we write a function or method that takes a function as a parameter and or returns a function as its return value? What does it mean for a method to return a function as its return value? And finally, immutability. We're going to tackle this head on. When I mentioned strings earlier in the semester, I'm like, let's just pretend strings are on the stack because that's how they behave. But we're going to talk explicitly about immutability, why strings are actually on the heap, but why they behave like they're on the stack. And we'll take a look at our heap and stack diagrams again to show the effects of immutability and what an immutable object actually does, how it's represented in the heap. They are all in the heap, but their state can never change. So we never have, when we do pass an immutable object by reference, we're just giving a reference, and then the method that is being called is going to that spot on the heap and accessing the data, the state variables stored in that object. But since those variables cannot change, we don't have to worry about any side effects of that method call. We don't have to worry about it changing something on the stack. So with that property, how do we simulate those changes? So if I want to remove all the commas from a string, for example, how does that represent? And we'll see that that creates a brand new string object and returns a reference to that new object that was created. Same with lists. We're going to creates a new list every time we add an element. Every time we prepend an element to a list, it creates a brand new list on the stack, or sorry, on the heap, and returns a reference to that brand new list that we created. So we'll talk about that in maybe more depth than you ever wanted to know. We're going to spend two full lectures strictly on immutability. And the homework assignments, I'm still working on the description of one of them. Hopefully I'll be able to introduce them properly on Wednesday. But you won't be able to use any mutable values. So no var and no objects that change state. So somewhat the opposite of the current homework assignment, where we're doing everything with state. That's what happens when we don't have state. And then later in the course, really it won't be until we get to event-based architectures, they'll start seeing the benefits of, okay, what is so bad about state in certain applications that we don't want state. And the quick summary of that is when we have multiple things happening at the same time, working on the same object, working with the same reference, going to the same spot in memory, what if one of those is changing the state of that object while the other one is computing on it? We can have some big problems when that happens. But if that object's immutable, that problem goes away. It's one of the very strong advantages of immutability. Oh my goodness, where are we? We're in this one. So with all that in mind, let's talk about sorting. Yes, you'll hear about sorting more than you ever wanted to know throughout computer science. It'll come up again in CC 250 for sure. In 331, it'll come up again. We like sorting in computer science. Don't ask me why, we just really like it. Before we get into new content, are there any open questions? All right, let's get into it. And sorting, each time you do hear about sorting, you'll probably hear about it in 4 or 5 different classes. The 4 I listed, this 115, 250, and 331, you probably see it in another one, I would imagine. Each time you do see it again, it's going to be to motivate a different topic. I think the reason we like sorting so much is because it's really easy to understand. Like, you know what sorting is, even before 115, you understand the idea of sorting. And then we use that background knowledge to show you the new thing that we're trying to talk about, which is going to be first order functions in today's lecture. So for this, the lecture question, unless you read on the slides or anything, won't make too much sense right now, but let's go through this. We want an object with one method, generic method, that takes a type as a parameter, takes a list of ints as a parameter, and takes a function from int to the value of the type parameter as a parameter. And then returns the input list, returns a new list, which is all the values of the input list, but with that function applied to it. There's a lot of words going on. When you actually finally write this method, it's only a few lines. There's not too much, but there's a lot of new vocab and a lot of new concepts through here, specifically to a type parameter and a function as a parameter, 2 brand new concepts. So we want to get our hands on that and just get you some experience with that. And the output list should be in the same order as the input list. And also a test suite. This is another one where the testing is probably a little more complicated than the actual code itself, but the testing is the other side of this. I want you getting practice with both sides. One, writing a method that takes a function and a type as a parameter, and then 2, calling that method. Calling this method that takes, what does it mean to, how do I actually physically pass a function to a method, and how do I pass that type parameter, that type, to a method? So let's talk about what all this means and what that's going to look like. So sorting, actual sorting, it's one slide without even any bullet points. Ordering elements according to some comparator. And the comparator is the key word we want to focus on today and on Wednesday. A comparator where, for example, if you just sort integers, you expect them to be from smallest to largest by default. But what was the comparator? How did we compare to ints to be able to get that ordering, and what does that even mean is the big focus. And sorting in Scala, if you just want to sort some numbers, we've done this earlier in the semester when we had to compare two lists for equality in our testing. We just called dot sorted, done. Lecture over, right? Dot sorted, and that gave us that default ordering. What's that? Oh yeah, there's a lot more slides. there's a lot more we got to talk about. But if we just want to sort a list of a known type for Scala, for example, ints here, or doubles, strings, if we want to sort those basic Scala types by the default ordering, no big deal, just call dot sorted. Scala's got us covered. The question is, what if we want to sort in a different order? And what if we want to sort our custom types? Those are the things we want to ask today. So with this, we use a default comparator, which is actually the less than function, is the default comparator for sorting ints and doubles. Whenever two elements need to be compared to be able to determine their order of each other, the less than function is applied. So if I need to know, does 5 go before 23? I'm going to check. Well, is 5 less than 23? No. Therefore, 5 does not come before 23. And I can check the other way around. Is 23, negative 23 less than 5? Yes. So negative 23 must come before 5 in this ordering. If both of those return false, I know I have an equality, and the order of those two doesn't matter. Depending on what sorting algorithm I'm using, it's going to order those differently. So I use the less than function, or the less than function is used here, to be able to determine the full order of this list. Now importantly, the less than function only takes 2 arguments. It's a binary operator, it takes 2 arguments and returns a Boolean. So if I want to compare a whole list, I can only sort this by asking myself a series of questions. Does this one element come before this one element? Does this one element come before this one element? And then continuously ask that question with different pairs of elements to be able to determine the entire ordering of this list. This is what we call comparison sort, where we're just comparing 2 values in specific orders to determine the full order of the list. So what if we don't want to sort by the less than operator? Well, now, in Scala at least, instead of using sorted, we're going to call sort by. Sort by, and give it a function. And this is what we want to talk about today. So we're going to give it a function. Technically, you can give it a method as well. But I'll be sticking with function. As I'm saying that, I guess ABS is technically a method, but let's not do that. So sort by is going to take a function that takes one argument of the type of the list that we're sorting. So here we have a list of ints, and I'm giving sort by a method, a method in this case, yes, technically, math.abs, which takes an int and returns some value, happens to be another int in this case, and then I'm going to sort on the return values of this method based on the default ordering of the type that's returned. So I'm going to sort using the less than operator, but before I sort on the less than operator, I'm going to take the absolute value of every element in my list. And this should look familiar from 115. You did this in Python, you did this in JavaScript. You said sort using this comparator. In Python and JavaScript, different syntax slightly. Python, you define the keys and sorted by that. JavaScript is more like what we're doing here, or what we'll do next actually, using a comparator. But you've seen this, and you pass that function. So this is slightly familiar, at least at this point. And we can do this, and you did do this. We'll do this. Oh, I got to update this slide. Over the next 2 weeks, we'll be doing this quite often. So this is a first order function. We just gave I might as well say it the right way. We just gave a method to another method but what happened in that call? So we've done this part so far in 115, but what happens on the other side is what we want to look at for the rest of these 2 weeks. So like I said, that was still the default ordering after that method is applied. We use the default ordering of the output of the ABS method. But what if we don't want to do that? What if we want to get more advanced, more tricky with this? Not that we're getting too tricky right here. There are easier ways to do this specific example. But what if we did want something more complicated and more custom in our sorting? So what if I want to sort by decreasing order? Well, I want to sort using a different comparator other than less than. So in the previous slide, we didn't use a different comparator. We just modified the values before sorting. Here we want to use a completely different comparator. For that, we're going to use sort with in Scala and pass a function that takes 2 inputs of the type of the list that I'm trying to sort and returns a Boolean. So what just happened here? Here's some new syntax, some new stuff that we haven't quite seen before. This, again, is a first order function. And this one is actually a function. I'm using that word properly. Math.abs technically was a method. This one is a function. This is a first order function. And we use this different syntax. Of course, each language is going to have different syntax to define them. Here's Scala's syntax to be able to define a first order function. This one happens to take 2 ints because that's the type of the list that I'm trying to sort, and returns a Boolean which fits the description, the definition of a comparator, similar to like you did in JavaScript. We don't need a -1, 1, and 0. I'm like 90% sure that's how JavaScript does it. We don't need the 3 different values. All we need is a Boolean saying, does A go before B? And that's all we need. So if A is greater than B, then A has to come before B, and then false otherwise. So false on a tie, false if B comes before A. And then we can call it twice to figure out if it's a tie in ordering. So that we can rewrite this. I just want to rewrite this to make this explicit of what's happening here. Because this is what I want to talk about, is this first order function. So we can pull this out instead of defining it inline. So before I just had this definition of the function right here where I had comparator. Here I'm just separating this into 2 lines. It looks a bit more complex, but I want to talk about all the syntax involved here. So I pulled that out of there, stored it in a variable, and then passed the variable into the sort with method. So I'm saying sort with this comparator. It's a function with the right definition, and I pass that function into the method. And yeah, we can do this. This is the magic of first order functions. They're just values. So let's take a look at the syntax here. To define a function, remember a method, we always said method when they're attached to an object. When we use the keyword def, we're inside a class or an object and we say def some method. Those were methods and they were always attached to the object that we were creating, or if it's part of a class, it'll be part of the definition of the objects that we create using that class. Functions, these are not associated with any object. So to declare a function, we're going to give it the parameter list just as though it were a method. Just the parameter list though, no name for this function when we're defining it. Just the parameter list in the same syntax that we've seen. And then instead of equals, just equals, we use this arrow notation, equal, greater than, to give the definition of the function. We're not assigning this to the parameter list. We're using this special syntax, kind of similar to the map syntax, some key to a value. some parameter list to some function definition. So we use this arrow syntax, just to make sure it's distinguished between this assignment operator here. And then the body of the method, or the body of the function. This is all the code that's going to be executed when the function is called. And same rules as methods, the last expression to be evaluated is going to be the return value of the function call. We can use a little bit different syntax, or rather the syntax that we're used to. We can have the parameter list, the arrow notation, like we did on the previous slide, and then use our braces that we're used to. We can shorten our syntax like this, especially if we have multiple lines for a function, we got to use this syntax. And in fact, if you have a method where its whole definition fits on one line, you can define that without the braces as well. That's valid, just valid syntax in Scala. So if you want to think of this as the methods that we've been writing the whole time, you can use this notation if you're more comfortable with that. But if it's a one-line function, it's common to just put that all in one line and keep the definition, the parameter list and the definition all in one line like that. Let's talk about the other side of this, the type of a function. So this whole thing, just in case it wasn't clear, this whole thing, this whole line is the same as any other variable we created with an assignment for its default value. We're saying, create me a value named comparator, begin the type, this is the type, equals some value, and this is the value. So the function itself is a value, and we can store it in a variable of the type of that function, and the type of a function needs to specify the types of its parameter list and its return type. So this variable comparator can store a function that takes 2 ints and returns a Boolean, and we're going to use that same arrow syntax that we used when we defined the function. We actually created the function itself. So we created a function and assigned it to some variable of a type matching that function, and then the sort with method is expecting a function that takes 2 ints and returns a Boolean. So as long as we have a value of this type, which comparator must have, or else we get a syntax error on this line, comparator must have that. It is that type, so we can give that comparator to sort with, and sort with whatever function we define. Of course, we're just sorting in reverse order, so we're not doing much with this power quite yet, but we can define any comparison that we want using this sort with and defining our own functions as our comparators. So this is the big thing that we want to talk about for 2 weeks, really, is a function is just a value. It has a type. It can be stored in variables of that type. It can be passed as, it can be used as parameters in a method of that type. It can be the return value of a method or function. You can have functions that return other functions. You have methods that return functions. You can have state variables of function types. You can use these anywhere. You could use like an int. Everywhere where you see int, you could change that to a function. And everything works just the same as you would expect. But these functions can move around our code just like any other values. They are objects. They're stored on the heap for what it's worth. And we can use them just like we would any other value. Any questions on that much so far? Because that's the crux. That's what like the next 2 weeks depends on, is that right there. So I want to make sure we go slow enough through this, make sure that it has time to sink in. Before we see, in 2 weeks of example after example, and of course we'll throw in immutability in there. Yes?
So is it like only the first order functions can be assigned a value, or the second order or third order functions can also be assigned value?
What do you mean by second and third order?
I mean, is it like just the first order functions
I mean, we can talk after lecture. I'm not quite sure. I'm not quite understanding your question, I suppose. So by first order, so this is what when I say first order function, this is what I mean is that a function is a value and it can move around our programs just like any other value. For example, Java can't do this. Java doesn't support first order functions. You can't just write a function and pass it around as parameters. Java has ways of getting around that. You create a class with a static method and treat it as a first order function. It even supports some special syntax to make it look like it's a first order function. I guess in a way that's what we're doing here too, to be honest. But there are languages that don't support first order functions, so that's the distinction. You can't do this in every language. But if you can move it around like just like any other value, then we have first order function support. It's different than the mathematical definition of first order function. Maybe that was your question? The mathematical definition of first order function is a different thing entirely. All right, let's see some implications of this. So first, for those of you tackling calculator, I gave that hint at the bottom. That's no longer an advanced hint, it's just regular stuff that you know how to do now. So maybe somewhere in your code, you want to store the next operator that's supposed to be used for any state, any situation that the calculator is in. That equal button is going to have some operator that it executes. What operator should it execute? Well, you can store that in a variable, some variable of a function type. And this is why there's no unary operators on the calculator. There's no factorial. There's no negate operators. There's none of those. Specifically so you can do this. You can take that binary operator that takes two doubles and returns a double. They're all in the same format. And store that in a variable as part of the state of your calculator. So without doing this, I've seen a lot of students have separate states for each of the four operators. I highly recommend doing it this way. Cut down the number of states, cut down your amount of duplicate code, and store the next operator that should be used in a variable, because that's something we can do now. And it can save you a lot of work and a lot of design complexity in your calculator. So what if we want to, I only have one slide on this one, but what if we want to sort our custom types? Same exact concept. So here I'm actually doing it with a method. I have a method that takes two animals and returns a Boolean, so we've satisfied the criteria here. And I want to sort animals by their name, ignoring case. Create some cats and dogs. They extend animal. The code is in the repo. I haven't talked about this one in lecture this semester. But it does what you expect. Animal has a name variable, and then cat and dog extend animal, so they all have that name variable. Get my list of animals, sort with compare animals. Then they'll be sorted alphabetically, ignoring case. So even if we have our own custom objects, our custom types, we just need a method or a function that takes two values as parameters of that type and returns a Boolean. As long as we meet that criteria, we can use sort with and sort our data structures based on that comparator. Well, how does it work? All right. It is quiet in chat. I assume it's a brand new topic. I assume this will take time to digest. Why it's so quiet in chat. But so let's see the other side of this. Let's revisit selection sort. This is something you've seen in 115, but I just want to do a quick reminder, quick overview of it while you're thinking about your first order functions, and talk about how we actually sort. In 115, I think it was like just part of one lecture. It was flashed by, and then you were never held accountable for that material. So I assume it didn't stick too much. So given some list, I want to sort it, and we're going to use the default comparator. We're just going to use less than. but I want to focus on how the less than comparator, how any comparator is used to be able to actually sort these values. So how do we sort? By only having a function that takes two values and returns a Boolean. How does that determine the full sorted order? So a selection sort, we're going to start with the first index in the list. We're going to find the minimum index, or the minimum value in the list, and swap that with the first value. So each time we're doing this, we're going to track the minimum value that we found so far. We'll start with the first value, say, okay, the smallest value we found so far is 5. And then go through the list. Okay, 5 and 23, pull up my comparator and compare these two. Does 5 go before 23? No. Does 23 go before 5? Yes. So now 23 is my current min value, or more generally, the value that I found that goes first in the ordering defined by this comparator. That's a mouthful. So according to this comparator, 23 comes before 5. So now 23 is my new thing that I'm going to compare the rest of the list with. Does 23 come before -8? Yes. Does 23 come before 7? Yes. Does 23 come before -4? Yes. Does 23 come before 10? Yes. I've reached the end of the list. Therefore, 23 must be the first element in the full sorted order for this list. So I can swap 5 and 23. 23 is locked in as the first value, and then I do the same thing with the rest of the values. Does 5 come before -8? No. Does -8 come before 5? Yes. Does -8 come before 7? Yes. -4, 10, yes, yes, yes. So -8 must be the next value. I swap 5 and -8 and repeat. So we go through the entire list doing this, finding the value that comes first according to the comparator that I'm given, in this case just the default less than, and just do that for every single index. By the time we get to the last index, we've got nothing left to compare. Technically my implementation will compare this last element with itself, so I kept that last thing in. Leave that 10 right there, and by the time we do this for the entire list, we have the full sorted value, the full sorted order. So the only thing we needed to do through all that, to change the ordering and change how the behavior works, most of that was the definition of selection sort, but the only thing we needed for a particular sort is that comparator. How do I compare two values? And then the algorithm takes that comparator that takes two values and decides how the entire list should be ordered by comparing pairs of elements at different times. So all I did was compare two elements each time. We use this comparator. So to do that, if we want to write selection sort to sort a list, we take some comparator as a first order function as a parameter in our parameter list. So now I don't just need to know what I'm sorting. If you want something other than the default ordering, give me a comparator as well. And then all of this code is the same. This is doing the swaps, finding the min element and doing the swaps and everything, iterating through those elements. All that good selection sort stuff. The only thing that changes if I'm sorting by increasing order, decreasing order, by absolute value, by the distance to 50, how close the number is to 50. No matter what I'm sorting by, I can use this same code. This code does not change. We're swapping out functionality and getting different functionality, different behavior based on the function that we're given as a parameter. And that's how we can change how we sort in these. So the same thing that sort with is doing, sort with is taking our comparator and doing the same thing. It's running its algorithm, using that comparator whenever it needs to compare two values, but these sorting algorithms are based on these comparators that just take two values and return a Boolean, and then sorts based on that comparator. So the only time I ever use that comparator is here, where I need to compare, where I need to check, does current value come before min found? If it does, this is the new min found. Everything else is selection sort in a very generic way. So this is what's happening on the other side of things. When we pass a function to a method, This is what's going on. That function takes that method takes a function as one of its parameters. The type is that type that we saw before, a function that takes 2 ints and returns a Boolean. And then we can call that function. We just use the name of the variable and then call that function using the typical way that we would call any method. Just call it with an argument list. And that gives us whatever that function does. We have no idea what comparator does. It depends on what the caller gave us. We have no idea what the value is, what actual function is in there, or even if it's a method. We don't care if it's a method or a function even. We're just going to call whatever we got and use that to determine the order. So if I want to sort by decreasing order, create a list, give it the greater than function, and now all my comparisons are doing the reverse order as what we'd expect from the default behavior. How do we sort it, man? Fun time error. Yeah, we don't really mess with null in Scala. It's a community thing, and we don't sort maps. I don't know if you're joking with these questions or not, but I'm going to answer them. Yeah, null. We really don't mess with null in Scala. If you ever have null in your programs, you're doing something that the Scala community doesn't really want you to do. We don't like null pointer exceptions in Scala. What's a type parameter? Good question. I got 10 minutes. Don't you get antsy on me? Type parameters. So the example that we just saw only works with ints. So that's cool and all, but what if I want to sort something that's not an int? I got to do something else. That's where we're going to use type parameters. So what if I want to sort these animals? I want to use my selection sort, just like we did earlier with sort with, but I want to use my selection sort algorithm instead of sort with. Not something you should do. You shouldn't use my selection sort method to sort anything because it's horribly inefficient. But what if we want to do this? How do we handle that? We're going to add a type parameter. So type parameter allows us to use the same method, but with a different type all throughout this method. We put our type parameters before the parameter list, and we use these square brackets instead of parentheses to specify that this is a type parameter. And we give it a name just like our other parameters, but that name is going to be a type at runtime. We've seen the other side of this with lists, maps, and all our arrays, our other data structures. We gave it type parameters when we created them. Now we're seeing the other side of that. How do we write code that takes a type parameter? And this is it right here. We're going to put the type right here, some value or some name for the type right here. And then throughout the definition of our method, we can use that type parameter. Now we don't know what that type is. We can't use any of the functionality of that type except toString in the any methods. We can't use any of the functionality of that type. We have to treat it completely generically, but we can use that type, especially if we have a function that works on that type too. So give me a list of some type and a comparator that works with that type. I'll return you a new list of that type. I have no idea what that type is, but as long as you provide me a list of that type and a comparator for that type, I'm going to run my sorting algorithm without even caring what that type is. I just don't care what that type is. I'm just going to sort your list of things based on the comparator that you gave me. We create a list of that type for our return. And the only other difference, there is no other difference. Our algorithm is exactly the same. We have completely generic code. And so we can sort any type by any comparator with one algorithm, which is how the library methods work. Like when they wrote Scala, they didn't know about our animal type, but it still worked just fine because it's using type parameters. And two, we don't have to test this thing again. We write this once in a completely generic way, and no matter what somebody wants to sort or how they want to sort it, they use this same code without any modifications. So we test this once, it works, and then we never have to change this code again unless we want to optimize our algorithm itself. Yes?
So are we assuming this is like all the same types, right? They're not going to input like an animal type and then
Yep.
a rocket type?
So this is just like a variable name. Wherever I say type, it has to be the same type. So this type has to match this type, has to match this type, has to match this type, has to match this type. All of those have to be the same. And if somebody calls this with a list of animal and a comparator that only compares dogs, they're going to get the syntax error. They won't even be able to compile. And we typically shorten these to just one-letter names. If you see type parameters, they're almost always one-letter names. So we shorten this to like a T or A, B. You know, there's a lot of K and V if it's a met. There are a lot of common shortcuts for these. But they're almost always single variable names, single character names. So now we want to sort this list of animals. This just works magically. So when we call a method that takes a type parameter, for example, when we create a new list, we're calling the list constructor a list of some things. We don't specify the type parameter as long as it can be inferred. So since I gave this a list of animals and a comparator that takes two animals and returns a Boolean, Scala's like, I gotcha. You want the type parameter to be animal. I'm going to set that type parameter to animal. You don't have to explicitly say it. I could have my brackets here and put animal, the class name. That'd be fine. But we don't have to as long as Scala can infer what type we want. For example, if this was a list of dogs that we want to sort with the animal comparator, we might have to specify the type parameter in that case. But as long as everything's consistent, Scala's going to figure it out and know that I want T to be animal in this case. So just a word of warning, actually, let me back up. Are any questions on this one? Let's digest type parameters here. I didn't even need the 10 minutes. So that might mean I went too fast. Can we use sort to filter out key things? Maybe. We use sort to filter out key things. We will use filter. We'll see how to filter based on a function that takes an instance of the type and returns a Boolean and create a new data structure based on that. You give an example of input. Other than this one. You know that we won't get runtime errors because Scala will check all the types at compile time. So as long as all the types are fine at compile time, it's going to compile, and then we won't get the runtime errors. The type parameters are checked at compile time. You give an example of the input. I'm not quite sure what you mean by that. Other than what I have on screen, you want another example? Or maybe you typed that before this slide was up. Any other questions? Like I said, with the data structures, we have been calling methods and creating, we've been using type parameters as users. We've been calling methods with type parameters all the time. Any list method takes a type parameter implicitly. We just don't have to specify it. And you know what, let me get to the code and show another example of that. But let me get this out of the way. Selection sort, I'm sorting, it's fine, but it's horribly slow what I just did. Selection sort itself, from 115, is an n squared operation. It's an n squared runtime sorting algorithm, which is bad enough, but our lists are immutable. And if you look through my code, I am creating a ton of lists throughout my algorithm. I'm pretty sure my algorithm ends up being n to the 4th if you look at it close enough. That's stuff that we want to fix. We'll talk about that on Wednesday when we talk about merge sort. We'll get rid of some of the runtime issues. And especially when we talk about linked lists in the data structures portion, how do we cut down the runtime of our list blow up? But let me go to the code and just show. Is this fine enough? I don't actually have a solution here. But if we go to into the list class, we're going to see type parameters on every method that we've had. We've been calling methods with type parameters all the time. Now we're just seeing the other side of that. How do we write methods that take type parameters? And with that, yeah, let's just end it there, and I'll see everyone Wednesday.